today's talk is definitely hands-on, and if you're here to come and make money thinking that I'm going to somehow provide the tricks on how to build cool RL algo trading systems, I think you're at the wrong place. What we are going to do today, however, is we're going to take a journey and sort of look at what RL kind of provides, especially considering all the noise that that's been going on with LLMs and agentic. It's quite interesting to see that the place is packed. Actually, I wasn't expecting anyone because of LLM. I mean, reinforcement learning has been around for God knows how long. So it's really good. Thank you very much, guys, for joining. But what we will do is do a walk through, some of the fundamentals of RL, and then we'll go to some toy applications actually, and then one demo, the last one, kind of looks into how you can build an algo trading system. It's not going to make you money, but kind of gives you some ideas on how to do this. So that's the plan, and thank you very much, guys, for coming. So without any further ado, this is who I am, and thanks a lot for the original intro there, but I'm from UBS. One other disclaimer, everything I'm saying here has nothing to do with UBS. So I'm not going to talk about what we do at UBS, trading strategies, all that kind of stuff. That's not going to happen. This is pretty much open source stuff. So everything I say here you can get on, it's open source. None of this is proprietary. So I just wanted to kind of call that out. And then if you guys want to reach out to me, these are my links. And with respect to the agenda, we're gonna, as I said, we're gonna kind of start off with looking at some fundamentals of RL. What is RL? How does it work? We'll then look at the different types of RL models that are out there, and then we'll kind of home in on pretty much what are known as model-free models or model-free RL techniques, and then we'll actually spend quite a bit of time on that because there are a number of different RL algorithms out there, and then we'll home in on some of the well-known or perhaps maybe not well-known RL frameworks that are out there in the Pythonic space. And then I'll kind of do a very quick overview of how RL is being used in finance, some of the projects I've worked on, although I can't really divulge some of the proprietary stuff. And then we'll pretty much look at code. And I'll walk you through 5 sort of demos, ranging from really simple ones, toy things like the Grid World, Frozen Lake. These are all things you can get on Gymnasium. If any of you are familiar with the RL kind of simulation framework, it's been around for a while. It used to be called Gym under OpenAI. It's now called Gymnasium. So we'll look at a couple of those. We'll look at Grid World, actually is one little thing I just wrote, really basic. And then then Frozen Lake is a well-known one. There's the pendulum problem, a very interesting classical problem. And then we'll briefly look at the cart pole problem, more to do with how to sort of do hyperparameter tuning of RL. It's not very easy actually, by the way, but we'll look at that. And then finally, yes, we will look at this this financial application. So without any further, of course, and then Q&A. So without any further ado, let's start. So what is RL? Where does RL actually fit in to the whole space of ML, machine learning? So we all know that a lot of machine learning that we've been doing in the past typically have been supervised learning, which basically means that you have data, it's labeled, and then you're essentially training the model how to observe patterns based upon many, many examples of labels. This is pretty much most of what has happened in machine learning for a while. And then in some cases, there's no labels, but somehow the data itself has innate structure. So that would be typically what we call unsupervised learning. So for instance, clustering be one example of that. But there's another sort of area of machine learning, which kind of has been around for a long time actually, but not necessarily a very popular approach to getting the machine to learn. And I actually got involved in this very, very recently, perhaps the last 2 to 3 years. I mean, for a long time, I've always wanted to understand how does RL work. And it was actually a problem that kind of got me looking at this branch of machine learning. So what is RL? Typically, RL is kind of driven on the basis of this thing known as the NumFOCUS decision process, which is a way of trying to articulate what happens when you have, say, you start from a given state, so that state is something that's been perceived from an environment, and you have an agent operating in that state. So the agent then, based upon that state, then applies an action, and then that action essentially generates a new state. And for every action, there's a reward. Either you gain or you lose. And that's pretty much it in a nutshell. So in a nutshell, it's pretty much, you can say, trial and error. You have state, so you perceive state, apply an action, and then you get a new state and a new reward. And it just keeps doing that in an episode. So it keeps repeating itself within episodes. But it's probably a lot more than just that. So typically you would have, as I've indicated, you have your state and actions, that's fine. But also, as you move from one state to the other, there's a probability of transition from going from state 1 to state 2. There's a reward function. How do you know that when you move from one state to the other, that new state is optimal or not? So you need a way to kind of measure that. So you have a reward function. And then most interestingly, you also have this idea of delayed, you have this idea of a discount factor. Essentially, you don't want to get the reward immediately, so somehow you delay that reward. And this has been used a lot as a means to sort of drive that whole MDP process, the NumFOCUS decision process. So if I go on to this slide here, what is the main basis of MDP? So MDP essentially would imply that the next state is only based on the previous state and the previous action, and that's about it. Yeah, there's no other information other than the previous state and the previous action. And then that gets us to a new state. And what this diagram is depicting here is just saying that, well, you have three, you can call it 3 states. What it's also showing you here is the probability of transitioning from one state to the other. And so you have a baby or a child. What is the probability of the child currently playing to then want to eat? And then perhaps what's the probability of it eating and then crying, and so on and so forth. And this, in a way, is a way how you can model sequential decision making. Yeah. So if I just go back to the original diagram I had about ML, ML could either be supervised, unsupervised, and reinforcement learning. There is a whole area, a space of problems where, as I said, not only you don't have the labels, but actually the decisions you're making are sequential by nature. And then to add on top of that, you're doing this in an environment that's uncertain. And RL actually lends itself really well in those scenarios. So just to kind of cut through some of the detail, the whole RL space is quite, there's a lot of models out there, or a lot of algorithms out there. So let's just kind of briefly go through some of the terminologies. So there's the model-free approach to RL, and there's the sort of model-based RL. I'm just going to quickly talk about the model-based, because we're not going to really delve into that in any detail today. The model-based RL are scenarios where the environment is well understood. So effectively, you understand environment dynamics. So it's possible to actually build a model that you can then essentially present to a machine, and it would understand how to make decisions. Even though there might be uncertainty, perhaps even the data itself is non-stationary. But in general, most problems do not follow that sort of, do not present themselves in that way. In general, in most cases, environment dynamics are not known at all. And this is where typically you would be using the model-free approach. So a lot of what I'm going to be talking about today will be pretty much algorithms or models that are in the category of what are known as model-free. So some of these you probably know already. Q-learning is one of them. So Q-learning, which is pretty much one of the most popular forms of RL. You perhaps also know about SASA as well, which we'll kind of delve into that a little bit. And then since the whole rise of deep learning over a decade ago, a lot of these classical models like Q-learning have now been able to introduce deep neural nets as function approximators, but to kind of make them a lot more robust, especially in cases where the dimensionality of the space, the problem space, either the action dimensions or the state dimensions are huge. Essentially, neural nets allow us to suddenly now, utilize the property of neural nets, which is the fact that they're universal approximators in that setting. And that's kind of, in a way, that's the birth of some of these other techniques or models, such as DQN, for instance. So DQN is just another version of Q-learning, but this time it's, you've got a neural net in the mix, and then you've got a whole bunch of neural network-based RL models, usually referred to as DRLs, so deep reinforcement learning. Yeah, and we'll look at that shortly. So as I said before, you have the model-based versus the model-free. And as I said, model-based typically are cases where you understand where you understand the environment dynamics. I was going to say market dynamics, environment dynamics. Also, one other thing typically is for most problems, you haven't got the transition probabilities. That's not known. It's not observable. However, in cases where you've got model-based RL, you do have the probability transition data. And then, as I also indicated, in most cases where the size of your action space or state space is small, then these techniques work really well. But you notice that majority of the problems that you tend to solve these days typically use a model-free approach. And most of the problems in fact, all the problems we're doing today will be looking at model-based algorithms. And why? So one of the things that they're good at doing is the fact that you can essentially, without not knowing anything about the environment, you could essentially just do what I showed you earlier, the trial and error, and just explore the environment. So you can apply a state and you get a reward back, you get another state, and you can keep doing this. But as long as your reward function somehow measures what's going on in that state, then you can actually get a lot out of a model-free approach. One other thing that you would tend to hear a lot about is this concept of a value function. A value function is just essentially a way of saying that when I go from one state to the other, there must be a way to measure that new state I'm in essentially has a certain value. Kind of implicitly relates to the reward, but not necessarily the reward. And rather than just the value function itself is not just based on the state, it also can be defined as a Q, state action function. So at times you might see, folks talk about the Q value function, which is a function of state and action. If I now quickly talk about some of the more common model-based algorithms, one of them is Q-learning, as I indicated before. Q-learning is a very, very popular model-based algorithm, and it's actually known as a value-based RL algorithm. So it's essentially, as you can see here, it adapts something called temporal difference. I try and not go into too much of the technical detail, but basically, the main takeaways are that Q-learning utilizes temporal difference. It also uses the value function as well as the Q value function. It is what's known as an off-policy approach, which basically just means that the action is not based on the current policy. Yeah, you see that shortly. When we look at the the Bellman equation. The other thing as well is, of course, as I said prior, all these models are sort of doing trial and error, but there's a balance between you applying an action as well as perhaps just applying a random action. So you have this exploitation and exploration kind of trade-off. And typically the way that's done is using this thing known as the epsilon greedy, where for some of the times, based upon this probability, you can choose to just make a random action, and in other times you actually make an action that's non-random. And this is essentially just describing the pseudocode, how Q-learning works. So you can see there that with Q-learning, you start off with a Q function, which is essentially set to, so depending upon the dimensionality of the problem, you have a Q matrix set to zeros initially, and then you have a number of episodes that you predefine. You then initialize your state, and then you just keep repeating in an iteration through each episode. You select your action and apply the action, get a new state, and then based upon that new state, you will then update your Q function. And this function here is what's known as a Bellman equation, effectively. Yeah. And the idea is that we keep repeating this, and as we keep going through a number of episodes, yeah, the Q function gets better and better. Yeah. One other thing as well, just to take note of here, is if you look at the Bellman equation here, you've got this thing here called max A. What that's saying is that when you choose the action is actually based on the maximum Q value. Yeah. And you see the difference between this, just take note of that Bellman equation there, and compare it to the next one, which I'm going to show you, which is SASA, which is slightly different to Q-learning. And that's the next thing we're going to discuss. So SASA, essentially, SASA just comes from the name of the different sequences of things you're doing. So you say state, action, reward, and then new state, new action. Effectively, that's SASA. However, SASA is an on-policy approach rather than what we had earlier, which is an off-policy approach. Okay? And you can probably see similarities in the in the algorithm. You can see here that just like before, we had the Q function, but this time, as you'd notice, the A, you have an A prime and an S prime. Okay? So rather than you getting the A that we had prior from taking the max of all the computed Qs, now, in this case, you're having to actually recompute a new Q and get the new A and new S to update your Q. That's the main difference between the two. And then that brings us to the deep or the neural net versions of these algorithms. So usually referred to as deep RL. So as I've indicated before, essentially what they've done here is you've gone from algorithms which were run pretty much for very low dimensional problems to cases where you want to run them on very large dimensional problems. And this is one area where neural nets really play a big role. I think the takeaways here are that the Q-learning, when combined with a neural net, is what they call a DQN. I think there's also a neural net version of SASA, but more interestingly is the whole kind of evolution of all kinds of neural network architectures are now out there. And to name a few, I've just given a list here of some of the ones that are well known. DDPG, which is actually a policy-based RL neural net. You got PPO, SAC, and there's so many different types of algorithms out there. Right. We're now just going to quickly look at the DQN approach. DQN actually, I guess from this slide, the main takeaway is that it's very similar to Q-learning, but the main takeaway here is that one, you now, because it's a neural net, not only do you have your S and A, but you also have, and your Q, of course, you also now have the weights of the neural net. So somehow you've got to train that theta there that's shown in here. The other thing is, part of the way it works is that you need to have this concept of what are known as transitions, sometimes referred to as trajectories. But what it basically just means is that you need a way to be able to replay experiences. Yeah, this is how it learns. Remember, unlike supervised learning, if you're trying to do, say, regression or say classification, using a neural net for supervised learning, typically you have labels. With RL, there are no labels. So you've got to create these so-called experiences. And that's the essence of this so-called experience replay. You get to see that shortly, when I show you the pseudocode. And then the other takeaway, I guess, is, the fact that with the replays, you are then having to then do an update of your weights based upon some loss function. And you see that shortly in here. So if you look at this pseudocode, this is essentially DQN. Most of it is very similar to what you saw earlier with Q-learning. The takeaways are, I guess, I haven't got what's going on there, right? You see what's going on there. So as I indicated there, you see at the start is the sample phase. The sample phase, you're just doing normal, that just works like a normal Q-learning thing. You run it, you state, action, and then you get your new state, you get your reward, and then you keep checking to see, are you done or not done? Yeah? You see that shortly in the code as well. Then, after a number of iterations of doing that, you build a memory D, okay? And then from that memory D now, what you then do is you then take a sample of memory D, a mini batch of that, and then you now use that to basically evaluate a target value, which is Y. Think of your target value Y as labels in the traditional supervised learning world, kind of, okay? And then that Y is then used to further, that's going to be used to learn optimal values of your theta. It's not shown here, but there's a theta. And that's what's shown here. So you see here that here you've got a loss function, and what you're doing there is essentially stochastic gradient descent to basically get an optimal value. And you keep doing this until you clearly get convergence. Yeah. So far I've talked about value-based RL. There's also this other area known as policy-based RL. And one thing I probably didn't mention, which I should have actually when I showed you the MDP thing, is that you have this concept of and so you have your environment, you have your agent. Your agent applies an action, you get state. You also get a reward function, but something needs to map your state to an action, and that's what's called policy. Interestingly, some of these architectures of neural nets could either be value-based or policy-based, and in fact, some of them could actually be a combination of the two. So you might have heard about things like actor-critic, architectures where you have a combination of the two. For policy-based neural nets, like things like DDPG or TD3, PPO, these essentially are not just using the value, but typically also use the policy. And you see that when we move on to the next slide, actually. Maybe just very briefly, DDPG is another form, another architecture. I find that it's a lot clearer when you look at the pseudocode rather than, but basically, its main thing is that it is both a value-based and a policy-based architecture. And that's very clear from this. So again, if you look at this, you see here that what's going on here, again, the top bit is very similar to what we've seen before. It's very similar. But what's going on here now is you actually have, rather than just your normal theta, you have a phi as well. So you basically have theta, which is going to be used for the weights of the value piece of your Q. And you also have your phi, which is going to be used for the policy. Okay? And then what you're doing essentially is just like before, you have your D. Remember, your D is this replay memory. It's a huge memory that you use where you've got a tuple of state, action, reward, blah, blah, blah. And then what you then do again here is you compute Y. You need to have like before, like a target. So you have Y in here. And then what you're then doing is that not only are you trying to now compute, remember this is a hybrid value policy. So you're computing two things here. You're updating the Q function and you're also updating the policy. And then based upon those updates, you can then use that to, again, through optimization, you'll use that to further update your Qs and your phis, which itself then is then used to get a better model, as you run through a number of episodes. So that's DDPG. Then you have the policy, and then you have the proximal policy optimization. This again is kind of similar to DDPG. Actually, one thing I should have mentioned is that DDPG is primarily used in the context of continuous action problem specifications. Again, I should have made that very clear. So when you do RL, you need to be very clear on the problem you're trying to solve, the actions that you're taking. Are they continuous? Are they in the continuous domain or are they in the discrete domain? Okay. So when we talked about DQN earlier, DQN is primarily a discrete action space algorithm. DDPG is typically used in a continuous space. PPO, I believe, can be used in both. Although it depends on which package you use. I think stable baselines, you can use it for both. We'll get to stable baselines shortly. Again, a better way to understand how PPO works is, again, look at the pseudocode. So this is what's going on inside the algorithm. So again, in this case, you also have both theta and phi, okay? The main difference here is this long bit there where you're essentially trying to clip. So you see you have this PPO clip objective function. And what that does is that actually solves some of the problems that you tend to have when you're using DQN, because DQN sometimes can be quite unstable. This clipping mechanism here actually fixes that. And then the other similarity here is that, again, just like before, you're having both the value as well as the policy, being updated, effectively. And then finally, we'll get into actually seeing how these things work. There is this so-called soft actor critic. It pretty much says it in its name. So it's very similar to the last It's very similar to DDPG. The main difference here, and you see it shortly, is that it uses like an entropy-based objective function. But basically, this is, again, used mainly in if you're solving a problem that has continuous action space. Again, I think it's better if we look at the actual pseudocode. So again, for this one, what is different? The main difference here, I would say, is the entropy. Where's entropy? So the main difference here is, I would say, is the update policy. So line number 14. That's the main difference compared to even what you saw earlier, PPO. But again, these are a lot of the architectures are very similar. And I think the main driver is being able to build an architecture where you're getting the best of both a value-based RL architecture, as well as the best of what you get from a policy-based. And then what you then do is you have this idea of actor-critic. So what's going on there is the actor will provide the policy, and the critic will check how good is that policy effectively. And then you keep just repeating that. And then in time, across a number of iterations, it gets better and better, effectively. Okay, so maybe after going through all of that, I can assure you there's no more equations. The rest of this now is going to be more hands-on. So I'm just going to quickly walk you through some of the well-known packages. So I don't know if some of you have used these, but the one that I think most people probably know about, I think, is stable baselines. Yeah, stable baselines is a well-known RL framework. I've used it, it's really, really good. The only problem is it kind of hides a lot of that detail, which is actually good sometimes, but it means that you don't really have to do that much coding. It hides a lot of that. There's another one that I use, which is not on this list, known as, it's called Machine, M-A-C-H-I-N. And I like it because what it does is, although it still does a lot of the boilerplate, you're still in control. When you define your networks, you do it yourself. You just use PyTorch, you do that. But it kind of allows you to understand the whole thought process that's going into the architecture. So those are the two I use, but there are all these other ones. And then I've just done a very quick survey where Neptune kind of, according to them, they've kind of, they've looked at these different packages based upon a number of criteria. And those are the criteria. And then what they've said basically is that Keras RL is the best model. The best package, according to them. Yeah. So what I think personally, from my experience, is it depends on what you're trying to do. In my case, I think I like stable baselines, especially once you've realized what you want to do, you've figured out what architecture you need to use. Stable baselines is really good to try and get stuff productionized very quickly. And it's really good in terms of hyperparameter tuning, which is a big problem in RL. It's very, very difficult to, you have a lot of parameters. You saw there that, these neural nets, these architectures have a lot of parameters, so you're gonna have to tune them somehow, yeah? So, in a nutshell, I've been using I've used machine and stable baselines. And for the demo, most of the work I did, apart from the first 3 demos, those were done without any libraries because they're simple, QLearn and Sasa. And even DQN is kind of simple. A simple DQN you can write yourself. But then when it came to more complex problems, I've resorted to using stable baselines. And I've also done one with machine as well, yeah. Okay, now we're gonna quickly talk about Gymnasium because I won't be doing any service. I think I might be confusing you guys once I start to show you the code, because how do we even build these RL environments? You need some kind of tool to help you simulate an environment, an agent interacting in that environment. So, Gym, or now known as Gymnasium, is a really cool package. I love it. It's really good, very easy to use. And you can build your own custom environments, and it's very easy. All you need to do is just subclass, the env class, yeah, and then just implement a bunch of methods like step. So and they're all intuitive, right? Step just means that when you run your, you run the, you're going through each episode, you apply a step because you're applying a state. From that state, you get action. Action then spits out a new state and a new reward. So step is where you would define all that stuff. You see it shortly. Reset is how you reset your environment after each epoch or after each episode. Render is how you render your, your environment either to screen in some cases. You see that some of these toy environments are very graphical, so you need to render them somehow. And then obviously close is pretty much what it says on the tin. Okay, right. I'm now gonna sort of do a detour and let's talk about probably what you guys really came here for, which is how do you use RL in finance? So this is just a list of some of the things I've done and some of the things that I like to do, but which other folks have done. And there is a lot of activity in finance, especially in, using especially deep RL. There's a lot of activity. So we're just quickly gonna go through some of these. So one big area is definitely algo trading, which basically just means a machine trying to do the trade. Yeah. So you feed it with a bunch of data. Typically, you feed it with price, price data from an index, and that could be price of assets, stocks, whatever. And then you do some feature engineering. Perhaps you would typically do things like you define some new signals, which you typically get from technical analysis. So things like moving average and something convergence, divergence. You would do all that kind of stuff, and then you can essentially create a customized environment using Gymnasium, and then you can run this stuff and then see how it fares with that data. Now, I must say this: trying to predict the markets, trying to actually trade is a very, very difficult thing. Yeah, it's extremely difficult. There are a lot of things that go on, which are sometimes just extremely difficult to model. But if people are making money out of this, they're not going to tell you how they do it. So what you see being published are just ideas. For you to really get your alpha, and it's known as alpha in the trade, you really need to do a lot more stuff than that. You also get to see these days that with things like LLMs and even in the past with NLP, they also try now to pull signals out of text data, out of news, etc., and then turn that into signals, into numbers, and then they can feed that into the RL model as well to be able to predict the market. Now, in terms of how they then use all these signals within the RL, they will typically and you see a very simple example that I did here. So typically, what you do is you would say, if the price is a certain value, or you might do a simple moving average, for instance. You say that if the price is past a particular moving average, buy or sell. Yeah. Now, what you now want to do is, rather than you do that, you want the RL to learn that dynamics. Yeah. So you would actually get the RL to take an action. The action could be buy or sell, and then it will come out with a buy or sell, and then you will then sort of either actually do the trade or not do the trade. And when I mean do the trade, I mean paper trading, as in you will the RL will since the RL has a neural net in it, the neural net, you give it a state, it spits out an action. The action will then be buy, sell, or hold, and then based upon that information, you will then work out what your reward function is, your profit and loss. That's pretty much what's going on. But what the main thing is how to define the states that you feed into your RL, i.e. the neural net, so that it spits out the right action. That's pretty much what's going on in that setting. Another area which I did more recently is RL has been used to do hedging. What do I mean by hedging? So when you are trading, you want to protect yourself from any sudden, market shocks, effectively. And so I looked at work I did. I was looking at option trading, And when you trade options, typically you're dynamically hedging. Yeah, you want to hedge. So dynamic hedging actually lends itself really easily with RL. So that's kind of one example. If you want more details, I've got all my stuff on my repo. It's called RL Dynamic Hedger. There's a lot of material on this stuff, by the way. When I did the research, there's a lot of papers. Of course, you have to go through it and figure out what's the best way. But yeah, so that's another area for doing RL. And then one other big area where RL is playing a big role in finance is portfolio optimization. So in cases where you want to figure out what's the most optimal way to compose a portfolio so that it gives you the highest return effectively. So it's an optimization problem. RL is really well known in this space, and there are a lot of papers. I've just given you like one or two here, yeah? And then one final area, which I know RL is quite big in, is order execution. So for folks who are doing algo as well, or just general machine trading, they want to have an optimal way of kind of executing their orders, their trades, yeah? So it's this whole space is known as market microstructure, where, volumes of trades and all these other things matter. And having an RL to understand that dynamics can really help in a big way. Hedge funds are doing this in a massive way. Of course, they're not going to tell you how they make their money, but something to know about, yeah? Okay, cool. Let's move on. So I've been talking now for 40 minutes. So I think we're pretty much very close to demos. But before I do demos, maybe I'll just quickly just go through this. And let's quickly talk about maybe some conclusions. Because I think when we do the demos, I'm going to be showing code. Let's talk about conclusions very quickly. So what are my conclusions, with respect to using RL for finance? I would say RL is really great certainly in situations where you haven't got the traditional sort of setting. You haven't got labels. You're making decisions sequentially. And in some cases, you've got the data that could tell you what's going on, but you don't really know what that data is telling you. So I think RL is really great at that. And in cases where, for instance, we know that there are market dynamics, could be geopolitics, it could be the market, market shocks. RL could be a very good way to explore what's going on, yeah? To give you, that extra bit of knowledge on exactly what's going on and potentially get you to shape your trading strategies. Okay, so that's one area. The other area I think is kind of linked to what I just said before. What's great about RL, when I did the hedging stuff, the hedging, RL for hedging, what's really interesting is that you don't need to tell it at all how it should do the hedge. The only thing that's really critical is your reward function. So as long as your reward function kind of truly measures outcome or your optimal outcome, you can literally just using Gymnasium, you can set this environment up and just get it to run, and it just runs through a whole bunch of episodes, which then leads me on to the problems with RL. RL is extremely compute intensive. You need to do a lot of runs, yeah? And also with that comes the problem of how to tune your parameters. That's a big, big problem, yeah? And I would also add that the reward function is no easy feat. You need to figure out how to define your reward function so that it actually truly captures your problem. Yeah, that's not very, very straightforward. That's a very, very difficult thing. And I think those are most of my observations. And then for me, future work, I actually put the algo trading thing together after my experience working on the hedging problem. And from what I've learned from playing around with this algo thing is that number one, trading is extremely complicated, okay? Number two, when you trade, risk management is critical, or else you lose lose a lot of money, okay? So risk management is critical. So So knowing how to measure your risk and figuring out how to hedge against risk in that setting is really, really key. Also, one thing that is missing in my approach, and in most approaches actually, because I'm not making money here, I'm just demoing it, is consideration for transaction costs. When you trade, there's actually a cost incurred, for every trade you do. So if you've got an algorithm that's saying, keep buying, and you're buying and doing many, many buys, maybe within a window, you have to balance that out with the transaction cost on those buys, right? So when I did the hedging thing, one thing that we also had to do there is when you're when you build a solution for hedging, you also need to not just consider the gains that you're making in terms of the fact that you're hedging against risk, but also at what cost. So there's a balance between reducing your risk, but also not increasing your costs. And that could be very, very interesting sometimes, or quite critical, or complex even, when you're trying to define your reward function. So that's a key thing to take away. What else? I think I've said it before. I mean, back testing is really, really key. A lot of the hedge funds, really, really put a lot of emphasis on back testing, and they do that, and it's very, very data intensive, very compute intensive. That's a big area. The demo I'm going to show you, there's no back test. Well, apart from looking at the numbers and saying they make sense, kind of, but there's no real back testing. I mean, come on, that's a big task. Yeah. Okay. Maybe at this juncture, I can, before I do the demos, if there are any quick questions, I can entertain any quick questions, and then we'll go into the demos. So up to you guys.
Quick question.
Yeah.
So a lot of the ingredients that you spoke about for reinforcement learning are like the same as in causal inference.
Okay.
Right?
Okay.
Because you have like maybe some population, you're providing some intervention or action, and then you have like a treatment effect that you're trying to optimize for.
Yep.
And
Yep.
I know
Yep.
that like the causal inference
Yep.
has its origins in like econometrics and finance as well.
Okay.
Are reinforcement learning and causal inference like converging into the same thing, or
It's a good question, and
different? And like when would you pick causal inference?
yeah. So I'm going to be very open with you. I mean, I'm not going to comment on things I don't know. So I know about causal inference, as in, I know it's another strand of our space, but I don't really know it's in that detail to make any commentary. Yeah. But it's interesting that you called it out. Yeah. Okay. Any other questions? Oh yeah. Sorry.
So trading is seen more as a short-term action.
Yep.
You also take long-term signals into account, like quarterly reports, cash flow reports, and get some signals out of them to give your model a better indication of holding as compared to just buying and selling.
Correct. No, you're right. So again, my response to your question would be more general. This again is to do with what I was saying earlier about when you are trying to build an RL solution for trading. First of all, what are you trading? Number two, what's your strategy? I mean, there are loads of strategies, okay? And then that I think will kind of shape and dictate what are your features. So remember that one thing that we saw there is that you need to have state. So something has to define your state. And then based upon state, then you have your actions. So you're right. I mean, in the demo that you're going to see shortly, the state was simply just actually just a price that we've just so took the price, did some feature engineering on it, turned it into some kind of signal, and then had three different types of signals, essentially just moving average and some other thing, and then that's pretty much my state 4. Yeah. So it had a state of dimension 4, and then actions were basically 3, dimension 3, buy, sell, hold. But in a more involved solution, I'm sure there'll be a lot more things you want to consider. And I believe what you said there is valid, correct? Okay, any other questions before so I think I'm doing well with time. Okay, cool, right, so let's now do the demo. This is a bit I dread, actually. Okay, so before I actually do the demo, just gonna walk you through it. So there are 5 demos. The first 2 are just toy applications. I mean, one of them I wrote, I basically looked at an implementation of the grid world, which is a well-known computer science problem, and I just kind of refactored it so that it works for me. So that's one problem. And I just did it because I mean, I'm not really a graphical person, but I just did something. And then a better implementation of that is probably what is in Frozen Lake. Frozen Lake is really cool. And then, and so that's the first demo. I mean, the first 2 demos. They will demonstrate some of the basic RL approaches, Q-learning, SASA, and also DQN, okay? And all those 3 approaches I wrote myself in Python. Yeah, it's quite straightforward. You can do that yourself. Then we move on to the third demo, which is where we have so actually the first introduction of a continuous action space. And I think for this one, I am doing the pendulum problem in Gymnasium. So the pendulum problem is a very interesting problem. So it's a problem where you have this pendulum that's inverted, and it's sort of like, the idea is to apply torque to it so that it goes all the way up and it stays there for a few seconds. And then that's the measure that it's worked really well. And actually, you'd be surprised. If you do it with just normal DQN, DQN it's quite unstable. So it doesn't really achieve the goal. Sorry, did I say DQN? And that's wrong. It's a continuous actions problem. Sorry, if you do it with, if you do it with kind of perhaps suboptimal RL models, you see that it doesn't really work very well. Even when I did this in stable baselines with even well-known models, I had to really play with it quite a bit, and I had to do a lot of performance hyperparameter tuning to get the right, to get the right parameters. So although it's a very simple problem, actually, the physics of it is kind of interesting. Yeah. So that's the third demo, and then the fourth demo is really just, I'm just going to show. I can't run the hyperparameter tuning because it takes forever. But I will show you how typically stable baseline is really good, and how I've gone about putting something together that allows me to do hyperparameter tuning. And then the final one is obviously this algo thing. Okay, so let's quickly go through each one. So and the first one, as I said, is grid world. This is pretty much it. So the action space is a grid, so you can either go left, right, up, or down. That's the action. The observations are essentially any spatial point in the grid. So the grid is 5 by 5, so there are 25 of those. And then the rewards are that if you hit any of the reds, then it just the game just terminates, right? It dies. If you as you go through all the whites, you don't get any reward. But the idea is to get to the green, and then when you get to the green, you get a reward of 1. Yes, it's quite straightforward. This is a well-known game. Okay. The next one is very similar. Frozen Lake. Frozen Lake, similar thing. Action space again. Left, right, up or down, and then the observations again are just based on the grid size, 16 cells, and then the rewards if you hit. So the idea is for this guy to get this, what looks like a present, I think. Yeah. But the thing is, the actual lake is frozen, and then these are meant to be, I guess, holes. Yeah. So if he goes in a hole, he dies, basically. All right. Okay. And then pendulum was one I just described earlier. So this is the pendulum problem. So it's a classic problem, classic control theory problem. It seems very easy, but actually it's not such an easy thing to solve because there's a lot of physics going on here. Yeah. So the action space is shown here. I think there are three values that go in there, and then observation includes all of these things here. The XY coordinates, theta, the angle theta, as well as the torque. Yeah. And then finally, not finally. And then the cart pole is just, as I said, this. I did this one because I wanted to just see how we can effectively do hyperparameter tuning, right, for something that is not normally that straightforward. Yeah. So again, this problem is a discrete action space problem where you're trying to move this thing left and right, and then you want to keep the pole upright effectively. I mean, I don't think there's anything else to say here. It's quite obvious. And then finally, we have, you know, the algo trader thing. So maybe I'll just walk you through this very quickly. So the idea here is that we want to, based upon knowledge of price, we're going to use S&P, the S&P index of prices. And what we're doing here is we're going to look at the close price of the S&P, and then we're going to use that to basically create a whole bunch of features that become state. And based upon that state, we either want to buy the stock, or we sell, or we hold. Profit is a fairly simple function. Profit basically is when we buy, we put it in an inventory, so that when in the next iteration, when there's a sell, you basically pick up what's in inventory and then you sell it. And then profit is basically looking at the current price minus what is essentially what you've just bought, and then that gives you a difference. Yeah. One thing which I've called out already, and it's in bold, I'm not considering any transaction costs. And actually, in the real world, that is a major, major thing you need to do. You must consider how much it costs to do trade. You know, to trade, it can eat into your whole, you know, your whole. I think they call it drawdown. Yeah. Okay. And then of course, I'm not doing any risk management. And these are all the, you know, the references, you know, if you're interested. So as I said, action space is, you know, 3. Observation space is essentially the lag. So what we have is not only are we simply getting each price, but we can also say that we also lag. So we can say we're trading based upon a window of data from 1 to n backwards, okay? And then of course you have a number of features. In this case, it's just 4 features. And as I said, the reward function is just a P&L, it's just profit and loss. This is the, that's S&P data that we're using. I think the data is from 2010 to 2019. And then just some basic things. So I use 80% of the data to train the RL, and then 20% to do the out of sample evaluation, i.e. test it. And then I'm just explaining here what I did in terms of features. So the main feature I'm getting from this data here is the close bar. I'm referred to as the bar, the close bar. And then that bar is then transformed into a number of features. So you can do the log return on the, log normal return on the price. You can do a 10 window moving average backwards. You can do a 10 window moving average of the log return. You can also do a 10 window moving standard deviation. These are all just different ways of creating features that truly provide signal to help you make the right trading strategy or decision. And there are loads of those. I think that's it. And then this is just showing you, so I did this because I can't really run this, because to get this, I have to run it for a while. So I did this just to show you that, you know, when I run this for a lot of epochs, it is a little bit unstable. And I guess, just what I was saying earlier, that when you do RL, you need to run these things for a long time. Obviously, if I'm doing a demo, I'm not going to run it for, so I'm just showing you a snapshot of, you know, what's happened. And this is where I'm using the PPO. So again, the reason why I went through all those different architectures is so that you can start to see how it fits in with what was done. So here I'm using the PPO model, and this was the outcome. So you can see it's starting to tailor. I mean, hopefully it's going to try and, you know, if I let this run much longer, at some point it'll probably start to converge, but it's going to take a while. And then this is just showing you when I train, this is the result I get. So what's shown here is the purple is showing you a buy signal, And the green, it's kind of like green, is showing you the cell. So what I'm doing is I'm just walking through the data and I'm telling you what action was taken as I walk through the data. Remember, this is the 80% of the data, yeah? And then when we do this, we then compute the P&L, right, the profits, to see how much money we've made. And here is just saying total gains is 14,000. Actually, disclaimer, I mean, this was the one I ran for a very, very short number of episodes. In reality, I probably need to let it run much longer, okay? And then now that we've trained the model, I then take that model and then I now use it to do the tests. And now I apply that on the 20% that's left of the data. And again, this is just showing you the buy and sell signal, and it's showing you what what profit was made. So that's essentially, what I've done. Now let's look at it. So I'm going to start with and please bear with me because I'm really dreading doing the. So I wanted to do all of this stuff on in the Jupyter notebook, but what I realized is that unfortunately, if you've got any videos or things that are visual by nature on Windows, if you run that in the Jupyter notebook, it just keeps dying every minute. And I wanted to move all this stuff onto Colab, I just didn't have enough time, so apologies. I'm going to have to run this through my unit tests, but you still get the gist anyway, okay? So we'll start with the first one. So the first one is, as I said, really simple. So the first one is this grid world. Hopefully you can see the code. Let me run it first, and then I'll walk you through the code. So let me just try and run it. So I'm going to just try and run this. So the first thing I'm going to do is, let me see. Okay, I think, yes. Okay, so that's grid world. So what I'm doing here is I'm just trying to show the contrast between a random agent, i.e. an agent has this is not Q-learning or anything, this is just a random, just get it to figure out how to come out of this. Yeah, so that's a random agent, and you can see it's doing very, very badly. It's doing extremely badly. Yeah, okay? And if we compare that to, and that's just showing you the reward function there. And if we compare that to a Q-learning agent, okay? So let's do that. Oh, okay, sorry. Yeah, okay, that's fine. That's just me running it, but now let me get to visualize it. So here I'm just running it just to show you to show you some of the reward curves. So there you can see the top curve is just showing you, at times it is hitting the 1 and at times it's not. But after a while, it's probably better to look at the bottom curve. The bottom curve is a moving average smooth curve. And there you can see it starts to taper and it starts to converge. And that tells you that it's learned, okay? Let's see if that's actually correct. So now if I now run this evaluator bit here, evaluate, I should say, here. Hopefully that is right. There you go. So you can see every time he's getting it right. For every, yeah, you see? So compared to the random thing, after a while this is learned, and it's now, and all it's doing is just simply learning how to get the optimal Q. If you guys remember, we had that Q function, which is from the Bellman equation, and that Q thing, you have to go through a number of iterations to get it right, and then after a while you get the optimal Q. And then what the other graph was showing you was that essentially it would converge after a number of episodes. Yes, please. Sorry? A trade?
Training and test split.
Yes, it is based on training, yes.
Right.
Yeah, it is. So, sorry, yes, of course, you're right. Maybe I should have made that clear, yeah. So what we're doing, let me show you the code so that you can see that. Okay. So the code, so if you look at this unit test here, there should be a run. Let me see if yeah. So here, So this is the agent, right? And inside this agent, there will be a, let me get you the, okay, hold on. Okay. I just want to show you where we're doing the training. Yeah, here. So you see here where we've got update cube table? This is us basically training it. And this is pretty much that Bellman equation you saw earlier. So remember you got Q is a function of S of A, and then you then update that with the previous Q of S of A plus the reward plus the discount multiplied by, yeah? That's basically this, yeah? So that's training basically, yeah? So that's where you're training the Q. And then what I then do is after I train, I then persist the Q as a pickle file, and then I now evaluate it. And the evaluation is the bit you saw when I run the actual graphical bit. Yeah? Okay, cool. Any other questions with this? Okay, I'll move on to the next demo. Oh, yeah. So, good point. So, for the first two demos, I just wrote that myself, right? Because there's no need to write. I mean, Q-learning is very easy. I mean, you saw the pseudocode. Yeah, you could literally implement that in Python. So no library at all. The only bit where I might have used a library is when I wrote my own grid world. Remember I said grid world? I used Gymnasium. Remember I showed you something about Gymnasium where you have to subclass the event class to create your own environment. But in terms of the actual RL, no. I mean, it's no. I didn't use a framework at all for that. Okay, we're going to move on to the second demo, which I think is Frozen. Okay, let me just close this down. Frozen Lake. All right, Frozen Lake. Okay, cool. I need to remember how. All right, so Frozen Lake. What I'm going to do here is just show you. I'm just going to evaluate it actually. So I'm going to evaluate Frozen Lake. I'm going to evaluate it using, starts with Q-learning. That's this test here. I'm then going to move on to SASA, and then finally move on to DQN. And you'll be able to see the contrast between these three different approaches to doing RL. So let's start with Q-learning. So first one is Q-learning. Again, please stop me if you need me to clarify anything. All this is doing here is just pulling, again, because of time, I'm not going to train this thing. And so I'm pulling it from a pre-trained thing that I've saved into a pickle file, and I'm just using that Q, the Q matrix that was pre-trained prior, and then I'm going to just evaluate it for you so that you can see it running. So this is the one, this is just Q learning, yeah. So there, now, let's see if it works. Honestly, yeah, it is. You're right, and I think I mentioned that actually. So what happened was initially, I wanted to do it myself, yeah? But then I realized that in terms of the graphics, it was just rubbish, right? I mean, you saw the grid problem, it's kind of rubbish. This is a lot better, but also what's great about this is that you have a lot more features in this. So for instance, you can set you can actually set it so that the lake is slippery and a whole bunch of other stuff. You can add a whole bunch of additional dynamics to the problem. So this is a lot more, yeah, and there's quite a lot to this actually. And the other thing you can do as well is you can change the topology of the whole lake. You can add more things in there, etc. I mean, I saw one demo on YouTube where the guy had done, actually it's quite interesting what he did. So that's why, I took it, yeah. Okay, so that wasn't very great. I mean, you saw that, although I think the first episode it got right, I think there were like 5 episodes. I think the other 4, at least I saw one where it went inside the, inside the hole. So that wasn't great. Let's look at SASA. Now this is using the SASA model. See, it's thinking, it's wasting a lot of time. Died. I mean, I'm not going to waste your time because I know. Okay, you see, so it's kind of close, but it's not there, right? It's trying to get to the target. Okay, got it. Got there. So for most of the episodes, it kind of gets it wrong, and I'll show you why in a minute. You see why, because if you look at the reward curves, you see why that these two are not so great. Okay, so I'll stop this one, and then I'll just quickly, in the interest of time, I'll stop this one, and we'll now do DQN. Now, DQN is a neural network-based approach. Neural nets are great because they can solve high-dimensional problems and all that kind of stuff, and they're universal approximators. So let's see how that fares. So if I do DQN, look at that.
So what's slippery off for this one?
No, slippery. Okay, good point. No, slippery is switched. So you're right. So I've switched it off. It's set to false. The reason why is because I need to do more training, and so I just kept it simple. Yeah, it's set to false. But that's just to show you the contrast between the two. Now let's quickly see why. If we look at the performance metrics, we can see why. I think I can quickly run that here. Let's see SASA. I think I can run. Yeah. So I think this will plot the performance metrics quickly. Yeah, you see. So that's the Q function being updated there, and then these are the graphs. So if you look at the graphs, you see a lot of perturbation going on there, right? It's not settling down. Yeah, you can see that that's not settling down. Yeah. So that's part of the reason why the learnt Q is not optimal compared to the DQN. Yeah. Okay. And then very, very quickly, if I just do the same with DQN, I'm not going to do Q because same thing. But if I do DQN as well, okay, it's just a bit slow. Oh, sorry. Let me bring this up. This is what I dreaded. Let's see if it's, yeah, you see, look, that's a lot smooth, right? This is DQN. See, look, it sort of tapers towards 1, which is the optimal value. Yeah. So why am I doing this? I did this because I wanted to understand fundamentally how these algorithms work. And I was just using a very simple environment to test this. But it was quite useful, actually, because even I was quite surprised at how bringing in a neural net into the equation can change things quite a bit. I'm going to move on now to, so far I've done the grid problem as well as frozen lake, and I think the gentleman there was right. I mean, they're kind of similar, although the frozen lake I think is much better artistically, and it's got a lot more features, like what you said earlier about you can switch on slippery to true, and that makes it even a lot more difficult to solve. Okay, so I'm going to move on now to another problem. This is a bit different. Let me just find it. So this one is the pendulum problem. Okay, and I'm going to start by just showing you. Yeah, okay. So what I wanted to do with this one is I just wanted to show you how, if you wanted to solve this, so this problem I solved using stable baseline. I didn't write the solution myself. I used a framework instead of writing the whole thing myself from scratch. Okay, but I also looked into how you can do this using the other library known as machine. So with machine, what I like about machine, this is what I like about it, is if you use machine, so right, this is just some commentary and blah, 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 and these are the steps. So I've got some helpers here to animate the thing, and then these are the steps. So if you use machine, these are the steps. So first thing you want to do, and, oh yes, of course, I should make it clear that what I'm doing here is I'm trying to use the DDPG approach. So I'm using which is a hybrid sort of actor-critic, i.e. value-based and policy-based neural net. So first thing you need to do is you need to define the network, your actor network, your critic network, and then you need to bring them together within the actual agent itself, the DQN agent. So that's what this code is doing. So the first bit here is just some PyTorch. So that helps me define the actor network. Okay, this is what I like about machine, because you can actually, you have more control over what's going on. And then this is the critic network. It's very, very intuitive, I think. And then now this is the agent itself. So now the agent is what calls those two networks. So how does it do that in machine? This is how it does it. So in machine, all you need to do is just create your actor like this. And of course, you have not just the actor, you also have the actor and the target. Remember we looked at that, when we looked at those pseudocode things. For these architectures, you need to have the actual network as well as the target network, because you're going to, unlike supervised learning, you need to have something to target. You need a target, like a label. It's not really a label, it's a target. So these architectures have both the original network as well as the target network. Same as well for the critic. And again, just to remind you, the actor, that is what produces the policy, and the critic is what checks to see if that policy is actually valid. Yeah. Okay. And then all you then do is inside machine, this guy here belongs to machine. You just tell it that I want to use DDPG. This is a version of DDPG that does, come on. It's a much better version of DDPG. I think this does something to do with the replay. Anyway, think of it as a better version of your kind of plain vanilla DDPG. That's what this does. And then you give it those 4 networks that we defined earlier. You tell it what your optimization criteria is. In this case, we're using Adam. And then you tell it what your loss function is. Yeah? And that's pretty much it. And then now, what I like about machine again is you take control of how you want to define what's going on when you train. So now, when I train the neural net, what I'm doing is I'm iterating through these episodes. I'm setting up a whole bunch of values in here. I reset my environment. It's always important to do that for every time you start an episode. I then, and then this is just pulling out the state, turning it into a tensor, a PyTorch tensor. And then I then start the inner loop. The inner loop is the bit that's doing actually going through the, the grids you saw earlier, is going through each one, and then within that guy, you're then gonna get your action based upon the state, you see? So this line here is basically getting the action, and then with that action now, we then get the new state reward, as well as a bunch of other things like, has it terminated? Is it done? And and the final thing in this tuple is the info. This is all to do with gymnasium, okay? And then you get all this data back. And then finally, what you then do is you then need to convert the state back to a normal NumPy array. And then as I demonstrated when we did the slides originally, you also then need to build your so-called replay. I don't know if you guys remember. That replay is called the trajectories. You have to build that thing so that every time you're running, you're building this replay, okay, which is a tuple of state, action, next state, reward, and has it terminated or not, okay? And then you do all of that. And then finally, now what you then do is at some point, as you run this, you then need to do an update. So in this particular case, the update is done when the episodes are more than 100, okay? And then that's actually when the neural net, that's when the model is now learning, essentially. It's doing all that stuff with the value network, as well as the target value network, and it's doing stuff with that, as well as the policy network, aka critic, as well as the target critic network. It does all that stuff that I think I showed you earlier with all those equations, and that's how it finally gets the right result. So this is how to run it in, if you're using machine, okay? I'm not gonna run it because as I said, I had issues when I ran this on Windows, but typically this is the results you get. And there you can see, this is the kind of response you would get. And this is actually getting better as you go through a number of episodes. Okay, now let's try and run this the easier way, which is using stable baselines. So if I use stable baseline, I'm just going to quickly run this that way. So if I run this here, let me try and. Okay, yeah. So I'm going to start with this one. I think this is all I need to do. Yeah, I think so. Okay, let's do it. I hope so. Yeah, there you go. So remember, this is the pendulum problem. So it's going to swing, but the idea is you want it to swing all the way up and stay. So that definitely worked. So that's using the version of the network, of the RL known as the SAC, the soft actor critic version. Let's now do the same with a DDPG. So, and pretty much it works the same way. I mean, all these were working really well. And there you see, yeah. And it stays. So just in the interest of, oh God, okay, let me move. In the interest of time, maybe I just, because I want to show you the, okay. So I'm going to move on now to the last demo, which is the trading one. And I know most people actually came to this talk for the trading. So let me show you that quickly. So this demo, what I'm going to do here is I will start by running this guy. Aha, yes. Okay. So the first demo is just going to show you what would happen if I run this. And again, I must say that what I've done here is because it takes forever to train this thing, I've just kept the number of episodes to something that's manageable. Yeah. So this would probably run in a few minutes. Yeah. So you see it's running, but if you look at what's going on here, so what's it spitting out there is a reward function. And actually, it does perturb a bit. You see that it's perturbing there. So what should be happening typically in an ideal world is the reward function should start to do this, start to get better and better and better. But actually, if you look at this reward function, just to kind of show you, yeah, this needs more training, right? This needs a lot more training, right? So you should be seeing what I showed you earlier in the slides. So if you remember in the slides, what we should be seeing is this. Is this. This is what we should be seeing, yeah? And in fact, this is still not enough. You have to give it enough episodes so that it starts to kind of, converge, yeah? But in the interest of the demo, I've just shown you that. But what's interesting though is that when you run it, this is the results I'm getting from training. So these are the gains from training. And these are the gains when we test it, yeah? And equally, so this is me using the PPO architecture. If I was to then repeat the same thing with another architecture, like the DQN, and remember the reason why I'm using these variants of RL, variants of the deep RL models is because the problem space, or at least the action space, is discrete by nature. So DQN is typically used for discrete. PPO can work for both discrete and continuous action space. So if I now run just for completeness, this actually doesn't do as well as the PPO. So you see there that it's getting, so if you watch these numbers here, which is the reward, actually the reward is going the other way, it's kind of reducing. So what I think is typically with DQN, especially if it's plain vanilla DQN, it does it is quite unstable. And I think what they've done is they've actually improved upon this architecture. So there's something called the double DQN, where they've found a way to kind of fix that. But also, I think what I should also say is that this requires a lot more training, right? It requires a lot more episodes. In the interest of time, maybe I'm just gonna stop here and entertain any final questions. Yes. Yeah, good question. So I'm gonna, I've already put the code in Git, but I'll put the code, the slides, as well as a whole bunch of resources. I'll put that all in Git in the next few days. Yeah, just give me some time, because, cool. Any other questions? Yeah.
Yeah, it seems that there was a bit of a difference in the toy examples where you don't have a reward until the end of the episode when it's either 1 or 0.
Yep.
I think if I understand right. And the trading example where every step you know what the reward is, right? Because you can measure your P&L at every step in time.
Yes.
Is that right? Does that change the problem when you have to wait till the end of the episode to know your reward?
Actually, in the toy examples, we don't know what the reward is. We just know that, that we kind of, up front, we say that, if you look at the grid thing, or the frozen lake thing, if the guy goes into one of those holes, then that's obviously bad. It's bad. And if if the guy goes into picks up the present, that's good. You're right from that point of view.
So you get that at the end of the episode, right?
You get that, yes, correct. Now with trading, I think that what you're trying to say is that with trading, you don't really know what your, correct. So with trading, this is where the reward function really matters a lot, because simply trying to get a high P&L, and if that doesn't factor in transaction costs or risk, then that's just, that's not giving the full picture, because you're going to lose money in the real world. Yeah, sorry, yeah. So have I Oh, yeah, good point. Okay, yeah, that's a good point. Yeah, correct. No, it's true. And that discrepancy, because I think it's a discrepancy, is to do with the reward function. How do you define, because the reward function has to really capture, what's going on in the market, yeah? But it's a good point. It's a good point. No, I haven't, and I think that's part of the back testing I think I need to do to really push this thing to its limit. Sorry.
How does the bot compare, say, buy and hold or dollar cost averaging?
Okay, so that to me strikes me as it's a good question actually, by the way.
It's very simple to do.
Correct. Yeah, true. I've not tried that, and I think you're right. There's a whole bunch of permutations that one could do to really push it to its limit and really see how effective it is. What I think I focused on in this exercise, and I guess for the talk, was just the mechanics, right? The plumbing. How do you put these things together? What's the right framework? Blah, blah, blah. I think there's a lot of work that one could do to really start to play around with, which is more domain specific. I think is more thinking about how when I trade, I just don't buy and sell willy-nilly. There's a lot of stuff you need to do, to think about. Correct. Yeah.
Why would you do something complicated when sitting there and doing nothing generates more return? Correct.
What I would say though is that if that was happening, a lot of people would be making money though, right? A lot of people are making money. So honestly, making money is not so, it's difficult. Sorry. Yeah.
Is it a Q, like an approximation of reward? If you have Q for each of the steps in the episode, it's just trained, if it's model, like machine learning model.
Yeah.
Just trained to approximate the reward at the end of the episode, isn't it?
Are you saying that the difference between the policy-based versus?
Q is approximated, a function which needs.
Yeah, true. No, you're right. Q indirectly measures the reward, but it's not really the reward. Yeah, it's a very. That took me years to understand that, because I've been looking at RL for a long time. It's only recently that I really finally figured out how to use it. Q is not the reward, but you're right. Q kind of implicitly can measure the reward function. Yeah.
I guess if I wanted to implement it, like using
Yeah.
some dense neural net,
Yeah.
I would need to
Correct.
Rewards from the end of the
Correct.
output.
Yes,
so
yes.
It's more or less.
Correct.
So I get it.
Yeah. What's good about it is that how you define the reward is really up to you. And I think that should come from, I think from what the gentleman was saying, that needs to come from domain knowledge, yeah? But in terms of the plumbing, how you put everything together, I mean, gymnasium, stable baselines, all these,
Or chess.
yeah, it's all out there, yeah? You know, you've got the infrastructure to do that. But I think the trick really is more to do with the reward function, which I think has to come from domain knowledge. Yeah, you need to understand what you're trying to do up front. Yeah. Anyway, guys, thank you very much, folks. Thank you.